Hello viewers, today in this part of the lecture we will talk about geometrical optics. The outline for today's discussion is as follows. We will start with the discussion of paraxial optics and we will discuss the matrix method to resolve the direction of the waves associated with the optical system. Then we will talk about imaging by spherical surface, then we will go to imaging by coaxial optical system, then we will discuss imaging by lenses, and finally we will talk about cardinal points and type of cardinal points. So, first we will start the discussion with paraxial optics. So, what is paraxial optics? A paraxial approximation is one when the incident ray makes a very small angle with the optical axis and the object is located very much close to the optical axis. In this condition, one can expect that the rays will meet at the same point after refraction from the optical system. The direction of the refracted ray can be completely determined from the following conditions, that is, the incident ray, the refracted ray and the normal should lie in the same plane, and the second condition is if theta 1 and theta 2 represent the angles of incident and refraction, then sin theta 1 by sin theta 2 should be equal to n2 by n1, where n1 and n2 are the refractive index for the two mediums involved. So, now we will discuss how we can bring in the matrix method to resolve the direction of the waves after it refracts from the optical system. So, using the matrix method one can find out the effect of translation and refraction, because the waves associated with any kind of optical systems go through two important parameters or two important observation, that is, one is through translation and the other one is through refraction. So, translation from the system can be represented in the following the matrix method, and that is the matrix of lambda 2 and x2 is equal to the matrix of 1 0 d by n1 1 multiplied with matrix of lambda 1 x1, and after refraction it becomes the matrix of lambda 2 x2 is equal to the matrix of 1 minus p 0 and 1 multiplied with the matrix of lambda 1 x1. So, the d, p and other parameters are described in the figure shown in the particular slide, and lambda 1 and lambda 2 are the wavelength in two sides of the optical system. Now, we will discuss about imaging by spherical surface. Now, let us image by a spherical surface separating two media of refractive indices n1 and n2 as shown in the figure in this slide. Let lambda 1 x1, lambda prime x prime, lambda double prime x double prime and lambda 2 x2 represent the coordinates of the ray at O, A prime, A double prime and I respectively in the figure. We will be using the analytical geometrical sign convention, so that the coordinates on the left of the point P are negative and on the right are positive. Thus, we can now represent the expressions in the following matrix form. The matrix of lambda prime x prime is equal to matrix of 1 0 minus u by n1 1 multiplied with the matrix of lambda 1 x 1, and the other two expressions of the column matrix by lambda double prime x double prime is equal to multiplication of the matrix of 1 minus p 0 1 with the column matrix of lambda prime x prime, and the third expression is the column matrix of lambda 2 x 2 is equal to the multiplication of matrix of 1 0 v by n 2 1 with the column matrix of lambda double prime x double prime, or if we simplify, then we can obtain the following expression, that is the column matrix of lambda 2 x 2 is equal to the multiplication of the following matrix, that is matrix formed by 1 0 v by n 2 1 and matrix formed by 1 minus p 0 1 into matrix formed by 1 0 minus u by n 1 and 1, and finally the column matrix of lambda 1 x 1. Now, after simple manipulation, the equation that we came out will give the following expression, that is the column matrix of lambda 2 x 2 is equal to the multiplication of the matrix formed by 1 plus p u by n 1 minus p and v by n 2 into 1 plus p u by n 1 minus u by n 1 and 1 minus v p by n 2, and that is multiplied with the column matrix of lambda 1 x 1. So, from this one can obtain the simplified expression, that is x 2 is equal to v by n 2 into 1 plus p u by n 1 minus u by n 1 into lambda 1 plus 1 minus v p by n 2 into x 1. Now, for a ray emanating from an axial object, that is for x 1 is equal to 0, the image plane is determined by the condition x 2 is equal to 0. So, in the above equation lambda 1 should vanish, and hence we get the following expression, that is u by n 1 is equal to v by n 2 into 1 plus p u by n 1 and n 2 by v minus n 1 by u is equal to p, and that is equal to n 2 minus n 1 by r. Hence, the matrix now becomes a column matrix of lambda 2 x 2 is equal to 1 plus p u by n 1 minus p and 0 1 minus v p by n 2, and this is multiplied with the column matrix of lambda 1 x 1. From this we get x 2 is equal to 1 minus v p by n 2 into x 1. So, the magnification is now given by m, and that is equal to x 2 minus x 1, and that will be equal to 1 minus v p by n 2, which after using the previous equation one can obtain m is equal to n 1 v by n 2 u. Now that we have discussed the imaging by spherical surface, we are in a good position to discuss the image formed by coaxial optical system. So, our next discussion is imaging by coaxial optical system. So, we would like to find out the image plane for an object plane at a distance minus d1 from the first refractive surface, and let the image be formed at a distance d2 from the last refracting surface. Now, the sign convention that we will follow is as before, where anything that is on the left of the first optical system will convey negative sign, and anything which is on the right of the second optical system will convey the positive sign. So, d1 is an intrinsically negative quantity. If d2 is positive, then the image is real and formed to the right of it. Similarly, if d2 is negative, then the image is virtual and formed to the left of it, as shown in the figure in this slide. Now, let us consider a ray O prime P starting from point O prime, which lies in the object plane, and Q I prime be the ray emerging from the last surface, and point I prime is assumed to lie on the image plane. Let lambda 1 x 1, lambda prime x prime, lambda double prime x double prime, and lambda 2 x 2 represent the coordinates of the ray at O prime, P, Q and I prime respectively. Now, once we know the coordinates, now we can easily write the equations for the matrix. That is, the first equation is the column matrix of lambda prime x prime is equal to the square matrix of 1 0 minus d1 1 multiplied with the column matrix of lambda 1 x 1. Similarly, the second expression is the column matrix of lambda double prime x double prime is equal to the square matrix of b minus a minus d c multiplied with the column matrix of lambda prime x prime, and the last expression will be the column matrix of lambda 2 x 2 is equal to the multiplication of square matrix of 1 0 d 2 and 1 and column matrix of lambda double prime x double prime. Now, having knowing these three expressions, we can simplify the above three equations to obtain the simplest single equation, that is the column matrix of lambda 2 x 2 is equal to the square matrix of 1 0 d 2 and 1 multiplied with the square matrix of b minus a minus d c multiplied with the square matrix of 1 0 minus d 1 1 with the multiplication of the column matrix lambda 1 x 1, where the first and third matrices on the right hand side correspond to translation by distance d2 and minus d1 respectively, and the second matrix corresponds to the system matrix of the optical system. So, after matrix multiplication, one can obtain the following equation, that is the column matrix of lambda 2 x 2 is equal to multiplication of square matrix by b plus a d 1 minus a b d 2 plus a d 1 d 2 minus c d 1 minus d and c minus a d 2, and this is multiplied with the column matrix of lambda 1 x 1. Thus, x 2 is equal to b d 2 plus a d 1 d 2 minus c d 1 minus d whole multiplied with lambda 1 plus c minus a d 2 into x 1. For a ray emanating from the axial object point, that is when x 1 is equal to 0, the image plane is determined by the condition x 2 is equal to 0. Thus, for the image plane, we must have b d 2 plus a d 1 d 2 minus c d 1 minus d is equal to 0. This will give the relationship between d1 and d2. Thus, corresponding to the image plane, we have the following equation, that is the column matrix by lambda 2 x2 is equal to the square matrix by b plus a d1 minus a 0 c minus a d2 multiplied with the column matrix by lambda 1 x1. For x2 not equal to 0, we obtain x2 is equal to c minus a d2 whole multiplied by x1. Consequently, magnification of the system m, which is equal to x2 by x1, would be given by m is equal to c minus a d2. Further, since the determinant of the square matrix b plus a d1 minus a 0 c minus a d2 is equal to 1. So, we obtain b plus a d1 minus 1 by c minus a d2 is equal to 1 by magnification m. So, in general, the expression of lambda 2 x2 column matrix is equal to the square matrix of 1 by m minus a 0 m multiplied with the column matrix of lambda 1 x1 correspond to image planes, where x1 and x2 correspond to the image planes. Now, we will discuss imaging by lenses. For a lens of thickness t and a material of relative refractive index of n, let R1 and R2 with a radius of curvature of two surfaces. Let the coordinates of the ray at point P and Q in the figure shown in this slide be the column matrix of lambda 1 x1 and the column matrix of lambda 2 x2. So, one can write the following expression by following the previous discussion, that is the column matrix of lambda 2 x2 is equal to the square matrix of 1 minus p2 0 1 multiplied with the square matrix of 1 0 t by n 1 and the square matrix of 1 minus p1 0 1 and finally, the column matrix of lambda 1 x1. So, in the equation P1 is equal to n minus 1 R1 and P2 is equal to 1 minus n by R2, that is equal to minus n minus 1 by R2, and this represents the power of the two refracting surfaces. So, the system matrix now becomes S is equal to B minus A minus D C, which form the square matrix, that is equal to a square matrix of 1 minus P2 0 1 multiplied with the square matrix by 1 0 T by n 1 and multiplied with the square matrix of 1 minus P1 0 1, and after multiplication we will obtain the square matrix of 1 minus P2 T by n and minus P1 minus P2 into 1 minus T by n P1, then T by n and 1 minus T by n P1. Now, for thin lens T tends to 0 and the system matrix takes the form of S is equal to 1 minus P1 minus P2 0 1 and they form the square matrix. So, for a thin lens A is equal to P1 plus P2, B is equal to 1, C is equal to 1 and D is equal to 0. So, substituting and solving the equation, one will get 1 by D2 minus 1 by D1 is equal to 1 by F, where F is equal to 1 by P1 plus P2 and that is equal to the n minus 1 multiplied with 1 by R1 minus 1 by R2 whole to the power minus 1, which represent the focal length of the lens. So, the system matrix for a thin lens is given by S is equal to the square matrix formed by 1 minus 1 by f, 0 and 1. So, for various lenses one can obtain different system matrix depending on the type of lens that is used for the optical system. Now, the final point that we will discuss is cardinal points. So, it consists of 3 pairs of points located on the optical axis of a rotationally symmetric focal optical system as shown in the figure in this slide. These are focal points, the principal points and the nodal points. These 3 will combine to form the cardinal points. These points will help in determining basic imaging properties in ideal systems such as image size and location. Here in this figure, f and f prime represent the focal points, p and p prime represent the principal points. So, the focal point is where any ray that passes through it will emerge from the optical system parallel to the optical axis. The rear focal point has the reverse property of the front focal point. An object infinitely far from the optical system makes an image at the rear focal point. For object at a finite distance away will make the image at some other point. A diaphragm at the rear focal plane can be used to filter ray by any angle. The 2 principal points have the property that a ray emerging from the lens appears to have crossed the rear principal plane at the same distance from the axis that ray appeared to cross the front principal plane. So, the lens can be treated as if all of refraction happened at the principal planes. These points are important as the planes through them help in determining the magnification of the system. For thin lens in air, the principal plane lie at the location of the lens. The front and rear nodal points have the property that a ray aimed at one of them will be refracted by the lens such that it appears to have come from the other and with the same angle with respect to the optical axis. So, the nodal points therefore do for angles what the principal planes do for transverse distance. If the medium on both sides of the optical system is the same, for example air, then the front and rear nodal points coincide with the front and rear principal points respectively. So, viewers, today whatever we discussed can be summarized by the following few points, and we discussed the concept of paraxial optics and the role of matrix method in understanding imaging. Paraxial optics is very important to understand to theoretically get the position of the image if we have an object which is very close to the optical axis and the ray emanating from the source is very much close to the optical system, and hence it does not form a very large angle with the optical system. Then we discuss the image formed by a spherical surface, and once we understood the image formed by a spherical surface, we discuss the idea of imaging by coaxial optical system. And once we know about the image formed by these two types of system, we went and discussed the image formed by lenses, which are integral part of any optical system that we have in our world. Then finally, we discuss the important concept of cardinal points, which is consisting of 3 points in the optical axis. I hope you would have liked today's lecture and you would have gathered important information regarding paraxial optics from today's discussion. Thank you very much for your attention.